In this video, we want to look at linear momentum and collision. Linear momentum and collision is what we want to look at. Let's look at the learning outcome. Learning outcome. At the end of this video, you will learn what linear momentum is all about. You will learn Newton's second law of motion, impulse of a force, principle of conservation of linear momentum, collision, types of collision, collision in two dimensions, and application of Newton's law and conservation of linear momentum. So this is our learning outcome. Okay, let's start. Linear momentum, what is it all about? So the linear momentum of a body is defined as the product of its mass and velocity. So we are saying that linear momentum of a body is the product of the mass m times the velocity v. So we have that linear momentum is mv. Let's call this equation 1. And linear momentum is a vector quantity. And from here, let's get the unit of linear momentum. The unit of mass is kilogram, and the unit of velocity is meter per second. So the unit of linear momentum is kilogram meter per second. Okay, let's look at this. Let's use this equation to solve an example. Let's look at an example of how we can use this equation. Okay, let me read out the equation. Calculate the momentum of a body of mass 77 kilogram, moving with a velocity of 20 meters per second. Okay, that's the equation we want to look at. Solution, we have to calculate the momentum P, we don't know, of a body of mass. We know the mass of the body to be 77 kilogram, moving with a velocity V of 20 meters per second. So using our equation, P equal to mv. So if we substitute 77 times 20, and that will give us 1,540 kilogram meter per second. Is that difficult? No. So it's good. This is how we use this equation to calculate linear momentum of a body. Okay, let's proceed. We want to look at Newton's second law of motion. Newton's second law of motion. Newton's second law of motion and linear momentum. We want to see how Newton's second law of motion and linear momentum is related. Okay. Newton's second law of motion states that the rate of change of linear momentum of a body is directly proportional to the external force and takes place in the direction of the force. So mathematically, Newton's second law of motion says F is directly proportional to the rate of change of momentum. So if we remove the constant of proportionality and we introduce a constant K, we will have that the external force equal to the constant times change in momentum. And from here, we'll have K. Momentum is mass times velocity. So from here, we will have this. And if we simplify further, we'll have K V minus U over T M. So we will have F equal to ma if k equal to 1 and acceleration v minus u over t. So mathematically, this is Newton's second law of motion. Let's call this equation 2. So this is the mathematical statement of Newton's second law of motion. Okay, let's proceed. We want to look at impulse of a force. Impulse of a force. The impulse of a force is the instantaneous response of an object to the force that acts on it. So impulse I is equal to force times time. So we have I equal to Ft. Let's call this equation 3. So we are saying that when force is acted upon an object, that instantaneous response as a result of that force, we call it impulse of a force. So it is given mathematically as I equal to Ft. Okay, let's use this equation to solve another example. For every equation that we get, we try to use it to solve a problem for us to better understand. Okay, let me read out the equation. John slapped his friend Tewase on the face, exerting a force of 200 Newton for 0.05 seconds. Calculate the impulse on the face. So that is the equation. Solution. We say John slapped his friend Tewase on the face, exerting a force of 200 Newton. So we know the force, 200 Newton for 0.05 seconds. 0.05 seconds. Calculate the impulse on the face. So we are looking for the impulse. We don't know. So after John slapped the friend Tewase, we are to find that instantaneous response as a result of what? The force that was applied on the face. So using the expression I equal to F times T, if we substitute, the force is 200 Newton times the time 0.05. So if we simplify this, we will have 10 Newton seconds. So the force that was applied is 10 Newton seconds. And this is the unit of impulse. The unit of force is Newton, the unit of time is seconds. So the unit of impulse of a force is Newton seconds. Is that taken? Okay, let's make progress. Let's make progress. The next thing we want to look at principle of conservation. Principle of conservation of linear momentum. Principle of conservation of linear momentum. Okay, the principle of conservation of linear momentum states that in any system of colliding objects, the total momentum before collision is equal to the total momentum after the collision, provided no external force acts on the colliding body. So that is the principle of conservation of linear momentum. And it is a direct consequence of Newton's second and third laws of motion. We shall be looking at that. Okay, so let's look at the principle proper. If you have two objects of mass, you have object A, the mass is ma, initial velocity ua, and you have another object B, of mass mb, moving with initial velocity ub. Let's say this is before collision. Before collision, let's say the two objects collide. This is upon collision. The two objects collide, and we will have that the force AB acting on the object. These are the two objects of mass MA, MB. So, after the collision, what happened? Let's look at it. After collision. After the collision, you have mass MA will be moving with velocity VA, the final velocity, and you have the second mass MB will also be moving with final velocity VB. So, according to the principle that momentum before collision is equal to momentum after collision. Remember, our momentum P is mv, mass times velocity. So for mass A, mass B, the momentum before collision is MAVA plus MBVB. According to the principle, it will be equal to MAV. Okay, this should be U, sorry, initial velocity. MAVA plus MBVB. Let's call this equation 3. Then the kinetic energy too will be half MAVA square, MAUA square, the kinetic energy before collision, MBUB square will be equal to half MAVA square plus half MBVB square. So this is what we are saying, that according to the principle of conservation of linear momentum, that if you have two objects A and B moving with initial velocity U, UA and UB before collision, upon collision the two bodies will collide, and after the collision the body of mass A will be moving with final velocity VA and body of mass B will be moving with final velocity VB. So applying the principle of conservation, that in a colliding object, the total momentum before collision is equal to what? Total momentum after collision, provided no external force is added. And the total kinetic energy before collision is equal to what? Total kinetic energy after collision. So this is the mathematical expression of principle of conservation of linear momentum. So we shall be using this equation to solve problems as we make progress in this class. Okay, the next thing we want to look at is collision. We want to look at collision. What is collision? What is collision? Collision can be defined as any event that involves two or more bodies coming together, resulting in a change in momentum and energy. So that is the definition for collision: any event that involves two or more bodies coming together, resulting in a change in momentum and energy. As we can see here, these are two bodies coming together, resulting in what? Collision, and as a result, it leads to change in momentum and energy. Are we together? So that is the definition of collision. Okay, then we have types of collision. Types of collision. The principal thing about collision is that the kinetic energy and the momentum. The linear momentum is the focal point for every collision. After two objects collide, either there may be a change in the kinetic energy and also the momentum. So let's look at types of collision. The first type of collision that we have is elastic collision. Elastic collision. What is elastic collision? In elastic collision is a collision between two bodies and in which the total momentum and kinetic energy of the bodies are the same before and after the collision. So a colliding object, like we have seen here, two bodies colliding with each other, and after the collision, if the kinetic energy before collision is equal to the kinetic energy after collision, and even the momentum before collision is the same as momentum after collision, we call that type of collision elastic collision. So a collision in which the kinetic energy before and after collision is the same, and also the momentum is the same, is called elastic collision. I hope you are following. Then the second one is inelastic collision. Inelastic collision. Inelastic collision is a collision where the total kinetic energy is not conserved. However, the total linear momentum is still conserved. So the difference here is that the kinetic energy is not conserved, meaning it's not the same, it's not conserved, while the linear momentum is conserved, meaning it's the same. So we are saying that in inelastic collision, the kinetic energy before collision is not the same as the kinetic energy after collision. But however, the momentum is the same, so it is conserved. So this is the major difference between elastic collision and inelastic collision. Then the third type of collision that we have is perfectly inelastic collision. Perfectly inelastic collision. Perfectly inelastic collision is the collision whereby the two colliding bodies stick together. As we have seen here, after the collision, if the two bodies stick together and move as one, we call that type of collision perfectly inelastic collision. As we might have observed, at times, even in football field, you see two players will collide with each other, and two of them will be rolling on the ground together. Or you see two vehicles colliding with each other, and two of them will stick together and move in the same direction. So that type of collision is called perfectly inelastic collision. Okay, let's solve some example to see how we use these formulas and the types of collision we have looked at. Okay, example. We are looking at an example now. Okay, example. Let me read out the question, then we look at it together. An object A of mass 10 kilograms is moving with a velocity of 5 meters per second and collides head-on with an object B of mass 3 kilograms moving in the opposite direction with a velocity of 6 meters per second. After collision, both objects stick so that they move with a common velocity v. Calculate v. So this is a question before us. How do we do it? Solution. We have an object A of mass 10 kilograms moving with velocity 5 meters per second and you have another object, object B, of mass 3 kilogram, moving in opposite direction with velocity 6 meters per second. And the two objects collide with each other. So the two objects collide, and we have them like this. This is the 10 kilogram, 3 kilogram, and they move with common velocity v meter per second. This is after collision. After collision, then this is before collision. Okay, so this is the question. How do we go about it? Let's start. Total momentum. Total momentum before collision, following the principle of conservation of linear momentum, the momentum before collision will be equal to momentum after collision. Okay, let's see. Total momentum before collision. So the momentum of these two objects before collision is equal to MA UA plus MB UB. So 10 times 5 minus 3 times 6. So that will be equal to 50 minus 18 equal to 32 kilogram meter per second. Okay, here, because they are moving in opposite direction, that is why we introduce this negative here. So if we look at it, this is the mass, this is the initial velocity. The mass of the second object, the initial velocity. So from here, we have gotten the total momentum before collision. So the next thing is now total momentum after collision. I hope you are following. Total momentum after collision. Let's look at it. The total momentum after collision is equal to MA VA plus MB VB. And this will be equal to MA plus MB into V. VA will be equal to VB equal to V. So here they have common velocity. Are we together? So from here, if we substitute 10 plus 3 V. So if we simplify here, we have 13V. So let's call this equation 1. And let's call this equation 2. So from here, we have that total momentum, using the principle of conservation of linear momentum now, total momentum before collision is equal to total momentum after collision. So let's substitute and see. So this is the total momentum before collision, 32 is equal to 13V. So by this, we equate equation 1 to equation 2. So if we simplify, 32 over 13 equal to V. So if we simplify this, we will have 2.46 meter per second equal to V. So this is the common velocity as the two objects collide. This is the common velocity with which they are moving. So this is perfectly inelastic collision. After the collision, they stick together and they are moving with common velocity. So this is the common velocity. If you observe, object A was moving at 5 meters per second, object B was moving at what? 6 meters per second. After the collision, the common velocity with which they are moving is 2.46 meters per second. I hope it's not difficult. Okay, let's look at another example for us to understand the types of collision, the principles of conservation of linear momentum that we just mentioned. Another example. Okay, let me read out the equation. A ball A of mass 0.4 kilogram moving with velocity 5 meters per second collides head-on with a ball B of mass 0.2 kilogram moving with velocity 2 meters per second. After the collision, A moves with velocity 3 meters per second and B with velocity 6 meters per second. Show that the collision obeys the law of conservation of linear momentum. That is the first question we have to answer. Is the collision elastic or inelastic? So this is the question before us. Let's look at it together. Solution. So we have two objects. The first one, A, 0.4, moving with velocity 5 meters per second. This object A. Another object B of mass 0.2 kilogram, moving with velocity 2 meters per second. This object B. And after collision, object A move with velocity 3 meters per second, while object B move with velocity of 6 meters per second. So this is before collision. Before collision. This is after collision. Okay, so what is the approach? Say momentum before collision is equal to momentum after collision. So total momentum. So we have total momentum before collision is equal to, let's solve that one first. It's equal to MA VA plus MB. Okay, let's use U, initial UB. Okay, let's make progress. So by substituting, we will have 0.4 times 5 plus 0.2 times 2. And if we simplify this, we have 2.4 Newton seconds. Okay, so this is the total momentum before collision. So total momentum after collision will be equal to MAVA plus MBVB. So let's substitute and see. 0.4 times 3 plus 0.2 times 6. So if we simplify this, we will also have 2.4 Newton seconds. So based on this, the total momentum before collision is equal to total momentum after collision. Have you seen the value? 2.4 Newton second, 2.4 Newton second. So the first question says, show that the collision obeys the law of conservation of linear momentum. So based on this result, it shows that momentum before and after the collision is the same. So by that, momentum is conserved. Okay, another way to prove it is before collision. Before collision, let's look at total kinetic energy now. I told us that momentum and kinetic energy is the emphasis here. before collision, the total kinetic energy, half ma ua square plus half mb ub square. So if we substitute, we will have half times 0.4 times 5 square plus half times 0.2 times 2 square. So if we simplify this, we will have 5 plus 0.4, which will be equal to 5.4 joule. Okay, after collision, the kinetic energy, let's look at that one too, will be half MAVA plus half MBVB square. Are we together? Okay, let's substitute and see. Half 0.4, half times 0.4 times 0.3 square plus half times 0.2 times 6 square. So if we simplify this, we have 1.8 plus 3.6, and this will give us 5.4 joules. So also the kinetic energy is the same. So the second question says, is the collision elastic or inelastic? So since the kinetic energy before collision is the same as kinetic energy after collision, the collision is elastic. Remember, we say in elastic collision, the linear momentum before collision is equal to linear momentum after collision. And the kinetic energy before collision is equal to the kinetic energy after collision. So we have proved that based on the value we have gotten here. So the collision is elastic. I hope you are understanding. Okay, let's make progress. The next thing we want to look at is collision in two dimensions. Collision in two dimensions. Collision in two dimensions. Most collisions are head-on. By that we mean a vehicle may be coming, another one may be coming. They will collide. We call that one head-on. Head-on. So most collisions are head-on, which is in one dimension. In one dimension. However, in reality, most collisions occur such that an object strikes another object at an angle. You have an object, another object will just come, strike it at an angle. This is another object. So collision at times can be head-on, like the ones we have shown in the example we solved, while at another point, collision can be at an angle. So for that, we call collision in two dimensions. So we want to look at collision in two dimensions. Okay, let's start with the types of collision that we have. Elastic collision in two dimensions. Elastic collision in two dimensions. Okay, if we consider an object of mass m1 moving with velocity u1, and we consider another object of mass m2 moving with velocity u2. And the two objects collide, and after the collision at a point A, the two objects collide, and after the collision, the first object is display of mass m1 move with velocity v1 at an angle theta. Then the second object of mass m2 move with velocity v2 at an angle, this theta 1, this theta 2. So this is an example of collision in two dimensions. You have y, then you have x. So this is an example of collision in two dimensions. Okay, so let's look at how we go about it for collision in two dimensions. Okay, since the collision is elastic, remember we are looking at elastic collision in two dimensions. So since the collision is elastic, both kinetic and linear momentum are conserved. So by principle of conservation of linear momentum, the kinetic energy E will be equal to half m1 u1 square plus half m2 u2 square, which will be equal to half m1 v1 square plus half m2 v2 square. So from the principle of conservation of linear momentum, the kinetic energy before the collision is equal to what? Kinetic energy after the collision. So this is the expression that we use to compute the kinetic energy. And since both bodies are moving towards each other in opposite direction, their combined initial momentum is given by, okay, initial momentum before collision. So before collision, momentum is equal to m1 u1 minus m2 u2. You know they are coming in opposite direction. That is the reason for the negative sign. So by the principle of conservation of linear momentum along the s-axis, we will have that by principles of conservation of momentum along the s-axis, this along the s-axis, we will have that m1 u1 minus m2 u2 will be equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2. So this is how we use. We resolve this. Are we together? We have looked at a resolution. In one of my videos, we looked at resolution of vectors. So if you resolve this into horizontal and vertical components, we have this. So this, the momentum before collision, momentum after collision. Okay, let's make progress. So since the body moves only along the s-axis, you know the movement is in the direction of s-axis. Before the collision, the initial momentum along the y-axis is 0. So along the y-axis, we will have that momentum before collision is 0, and we can resolve this to the vertical component, and we will have m1 v1 sine theta 1 plus m2 v2 sine theta 2. So if we know angle theta 1, theta 2, then we can determine the final velocity, v1, v2. So this is what we are saying, that you have two objects, m1, m2, moving in opposite direction, and they collide. After the collision, m1 move at an angle theta 1 with velocity v1. m2 move with at angle theta 2 with velocity v2. So we are looking at elastic collision in two dimensions. And I told us that the emphasis here is what? In elastic collision, that kinetic energy before collision is equal to kinetic energy after the collision. So this is our expression. I hope you are following. Then, let's look at the momentum now. The momentum before collision, we have this. Momentum before collision, since they are coming in opposite direction, that is why we have the negative sign. Then by principle of conservation of linear momentum, we say momentum before collision is equal to momentum after collision. So this is the momentum for the horizontal component. That is the x-axis. Then if we look at the y-axis, since the object initially was not moving along the y-axis, so that is why we have 0 here. But we can resolve this into both vertical and horizontal component. We have resolved to horizontal component and we have gotten this. So if we resolve to vertical component, we will have this. So with this expression, if we know theta 1, if we know theta 2, we will be able to calculate V1, V2 as the case may be. So this is elastic collision in two dimensions. Let's solve example to see how we use this equation. Let's solve an example to see how we use all these expressions. Okay, let me read out the question. A 1,500 kilogram car traveling east with a speed of 25 meters per second collides at an intersection with a 2,500 kilogram truck traveling north at a speed of 20 meters per second. Find the direction and magnitude of the velocity of the wreckage after the collision, assuming the vehicles stick together after collision. Okay, let's solve it. Solution, we say a 1,500 kilogram car. This is a road. You have a car moving and the mass of the car is 1,500 kilogram. And the car is moving with a velocity of 25 meters per second. As it is going at a junction, say at the intersection, collide at an intersection with a 2,500. Okay, at an intersection, this is the intersection now at a T junction. Another car was coming towards north in this direction, a truck for that matter. So let's say this is the truck that is coming. This is the truck of mass 2,500 kilogram. And it's moving with velocity of what? 20 meters per second. And these two vehicles collide at this junction. This is the point of collision. Collide at this point. And after the collision, at an angle theta, move with common velocity v. So we are to find the direction and also the magnitude of the common velocity. Okay, let's look at it, how we go about this. So momentum before collision is equal to, let's look at momentum before collision. It will be m1 u1, which will be equal to m1 plus m2 v cos theta. That is along the s-axis, change in momentum along the x-axis, change in momentum along the y-axis. In the case of the y-axis, m2u2 is equal to m1 plus m2 v sine theta. Let's call this equation 1, this equation 2. We have not done anything. We try to resolve this. We try to resolve this into horizontal and vertical components. So this is the expression that we have from the formula that we have earlier. So if we divide equation 1, divide equation 2, by equation 1, we will have m2u2 over m1u1, which will be equal to m1 plus m2 over m1 plus m2 v cos theta v sine theta. We have not done anything. You see, this and this we cancel. You will be left with v sine theta over, okay, including the v too. So you'll be left with sine theta over cos theta, which will be equal to tan theta. So from here, we can solve for theta. From this, you have theta equal to tan inverse of m2u2 over m1u1. Let's substitute and see. We substitute tan inverse 2,500 times 20 divided by 1,500 times 25. So if we simplify, we will have 53.1 degree. So that is the direction. From this direction, we have to find the velocity. So we can, since we have known the angle, we can use equation 2. This is equation 2. From equation 2 here, we can find v. So using equation 2, we will have that v is equal to m2u2 over m1 plus m2 sine theta. Okay, let's substitute and see. We'll have 2,500 times 20 over 1,500 plus 2,500 sine 53.1. So if we simplify this, we will have 15.6 meter per second. So this is what we are saying. You have two trucks, a truck moving in the eastern direction, another truck moving in the northern direction. Two of them collide and stick together. So we have to find the angle, the direction, and also the velocity since they stick together. So we said before collision, we resolve into horizontal and vertical axis. From there we simplify and we got the direction to be this. Then using equation 2, this is equation 2. We want to find the velocity, this velocity. So this velocity now, we substitute and simplify, we'll have this. So the velocity of the vehicle after sticking together will be 15.6 meter per second. Then the angle, this theta, will be equal to 53.1 degree. I hope it's not difficult. So this is how we go about with elastic collision in 2 dimensions. Elastic collision in 2 dimensions. Okay, let's look at inelastic collision. Inelastic collision, in two dimension. Inelastic collision in two dimension. Inelastic collision in two dimension. We have looked at the elastic collision in two dimension. We want to look at the inelastic collision. Let's look at it. Consider two bodies of masses m1 and m2 moving at an angle theta. We have two masses. The first one, m1, moving with initial velocity u1, and you have another mass, m2, moving with initial velocity u2 at an angle theta 1. Then they undergo a perfectly inelastic collision at point B. This is the point of inelastic collision. The two masses stick together to form a single mass, m, which then travel with a final velocity v, making an angle theta 2. Okay, after the collision, the two masses travel together as one mass, m, with velocity v at an angle theta 2. So this is an example of inelastic collision in two dimensions. Okay, how do we go about it? Since the collision is inelastic, kinetic energy is not conserved, and the linear momentum is conserved along x and y as follows. Okay, let's look at it. The kinetic energy is not conserved, and the reason is that it is inelastic collision. It is not conserved. So we want to resolve this into horizontal component and vertical component. So let's look at it together. The linear momentum for horizontal component for horizontal component, we have m1 u1 cos 0 plus m2 u2 cos theta 1, which will be equal to mv cos theta 2. So if you simplify this, you have m1 u1 plus m2 u2 cos theta 1 equal to mv cos theta 2. Let's call this equation 1. Then for vertical component, we have m1 u1 sine 0 degree plus m2 u2 sine theta 1 equal to mv sine theta 2. Sine 0 is 0, so all this one cancel. So you have m2 u2 sine theta 1 equal to mv sine theta 2. Let's call this equation 2. So if we know angle theta 1, angle theta 2, we'll be able to determine the final velocity v of the object. So this is how we go about in the case of inelastic collision in two dimensions. You have two bodies colliding at a point P at an angle theta 1. And after the collision, remember, it's perfectly inelastic collision. The two of them stick together at one, having common velocity, and move at an angle theta. So you resolve this into vertical component, horizontal component, likewise to this. So we say for the horizontal component, if we resolve, remember this is moving at an angle 0. That is why we have this. So if you resolve this into horizontal component, you have this expression. And if you resolve this to horizontal component, you have this expression. So if you simplify, cos 0 is equal to 1. 1 times this, you have this. That is why we have this equation 1. Then resolve into vertical component. So you resolve this into vertical component and this also into vertical component. So you have this expression. Sine 0 is 0. So everything here will be 0. You'll be left with this and this. So if we know theta, theta 1, theta 2, we'll be able to calculate the final velocity. So this is how we go about with inelastic collision in 2 dimensions. Okay, let's look at one example. The example will help us to better understand inelastic collision in 2 dimensions. Okay, let's go. Let me read out the equation. A football player of mass 53 kilogram moving with a velocity 15 meters per second at 90 degrees collide with another player y of mass 60 kilogram moving with a velocity 12 meters per second at 120 degrees. Calculate the magnitude and direction of the common velocity with which the players begin to move immediately after the collision. So that is the equation. Let's look at it together. Solution. We have a player of mass 53 kilogram moving with velocity 15 meters per second, and you have another player of mass 60 kilogram moving with velocity 12 meters per second. Then they collide. After the collision, this move at an angle theta, and they have common mass and common velocity. So from here, the first mass is at angle 90 degree. The second one is at angle 120. So from here to this point is 120. 90 minus 120. This angle now will be 30 degrees. Are we together? So let's proceed. Since the collision is inelastic, kinetic energy is not conserved, and linear momentum is conserved along x and y axis. Okay, let's make progress. We have an angle along the x-axis is 0 degree, this very layer that is coming. Then angle along the y-axis is equal to 120 minus 90, 30 degrees. That is what we have here. Then the mass, the total mass, will be equal to mass of player X plus mass of player Y. And that will be 53 kilogram plus 60 kilogram. And that will give us 113 kilogram. So the next thing now is to resolve into horizontal component. Horizontal component. If we resolve into horizontal component, we have mx ux cos 0 degree plus my uy cos 30 degree will be equal to mv cos theta. So let's substitute now. We have 53 times 15 plus 60 times 12 times cos 30 degree will be equal to 113 times v times cos theta. So if we simplify this, we will have 1418.5 equal to 113 v cos theta. From here, v cos theta will be equal to 1418.5 over 113, which will give 12.5. So v cos theta equal to 2.5. Let's call this equation 1. Then vertical component. Vertical component. For vertical component, we have mx ux sine 0 degree plus my vy vy sine 30 degree is equal to mv sine theta. So let's substitute 53 times 15 sine 0 degree plus 60 times 12 times sine 30 degrees equal to 113 v sine theta. If we simplify this, sine 0 is 0, so this one will go. We'll be left with 360 equal to 113 v sine theta. So if we simplify this, we will have 3.19 will be equal to v sine theta. Let's call this equation 2. So if we divide equation 2 by equation 1, we will have 3.19 over 12.55 equal to v sine theta over v cos theta. So if we simplify this, v will cancel v. This will give us tan theta. So theta will be equal to tan inverse of 3.19 over 12.55. So if we simplify this, theta will be equal to 14.25 degrees. So we have gotten theta, which is this, to be 14.25 degrees. The next thing is the velocity. So from equation 2, where is equation 2? Okay, this equation 2, we have that v cos theta is equal to 12.55. So from here, v will be equal to 12.55 over cos 14.25. So if you simplify this, we have 12.95 meter per second. Okay, so this is the velocity that we are to Fine. So all we are saying here, we have an inelastic collision. All you need to do, the angle, this moving at an angle 0, then this at angle 30. We are to find this and the final velocity, the total mass. Because they stick together, you have this. Are we together? So this is the total mass. So you resolve into horizontal component and vertical component. So for horizontal component, we say momentum before collision is equal to momentum after collision. And we substitute and have this. Then the second one, the vertical component, momentum before collision equal to momentum after collision. So we simplify and we have this. So from here, we get the angle theta to be equal to this. Are we together? Then the next thing is the velocity from equation 2. We are able to simplify to get this. So this is how we go about inelastic collision in 2 dimensions. Thank you very much for watching. Bye for now.